the world on our website, our magazine, and through social media platforms. I will try and put this notice up at the end of the meeting so people can see what the details are. Okay. So without further ado, then I'd like you to welcome Steve Barrett from Liverpool University to give his presentation, The Legacy of the Hubble Space Telescope. Thanks very much, Steve.
Okay, good evening, everybody. Can you hear me at the back okay? Excellent. So, as was explained earlier, I'm giving this talk from an iPad sitting on my lap, and I don't have a particularly good connection, so I apologize if my voice breaks up, or what is more likely is that there's a slight lack of synchronization between the slides and what I'm saying. I'll try and keep on top of that to avoid saying one thing and showing you something completely different. Okay, let's make a start and see how we go. There can be few people who don't recognize the Hubble Space Telescope. It's one of the few scientific instruments that actually is recognizable not just by every astronomer, but arguably by very large fraction of the general public. They might have heard about the Large Hadron Collider, but show them a picture of it and they wouldn't know what you were talking about. Hubble Space Telescope is different. It's an iconic instrument in itself, as well as the results that it's produced. So what I'm going to be talking about this evening is I'll give you a little bit of an introduction about why we need space telescopes and what are the alternatives that we could use on the ground. A little bit about the history of how the mirror was flawed and how the optics were eventually fixed a few years after it was realized that there was a problem. And the legacy, I'll talk a little bit about how it's extended our understanding of the universe. Though, of course, in a short talk, you can't possibly cover 30 years of science in only a few minutes, but I'll just touch on one or two items. And also in terms of the legacy, how it touched the public consciousness, how the public came along for the ride, as well as scientists getting an enormous amount of information from the telescope. And then before finishing, I'll just wrap up with a revisit to the future of space telescopes and the ground-based alternatives. So that's what we've got in store for the next, what's it going to be, 3 or 4 hours, Mike, something like that? Yeah, okay. Let's start with a picture of telescope sizes. It will give us an idea once the screen decides to update. There we go. This is an indication of the relative sizes of lots of telescopes, old and new. If you're struggling to get the scale, then there's a small human in the bottom right. I'm afraid I can't point with this particular screen, but there's a small human in the bottom right. And at the very bottom on the left, there's a tennis court, and on the right, there's a basketball court. So that gives you an idea of the scale. The very top left is the largest refracting telescope, the Yerkes Observatory 40-inch. Next to it, there's the Hale 5-meter or 200-inch telescope. And in the bottom left-hand corner, you can see the 4 space telescopes that I'll be talking about, mainly about the Hubble Space Telescope, but I'll also mention the other 3, Kepler, Gaia, and the James Webb Space Telescope. But you can see some of the other telescopes are very much larger in terms of the size of their mirrors. Currently, the largest telescope on the ground is the one in yellow in the top center, the Gran Telescopio Canarias. That's the 10-meter scope on the Canary Islands. And if you look towards the right, you can see the blue 30-meter telescope and the green European Extremely Large Telescope are absolute monsters compared to the size of the Hubble Space Telescope mirror, which is a mere 2.4 meters in diameter. You can see that 30-meter and 40-meter diameter telescopes are huge in comparison. So, of course, we all know as astronomers that telescopes have come a long way in 400 years since Galileo. A picture on the left shows the Yerkes 1-meter refractor. On the right, the Hale telescope with a 5-meter mirror at Mount Palomar on the right. And for all of those 400 years, there's been a push to make telescopes larger and larger. And there's a twofold reason there. Larger mirrors collect more light and hence allow us to see fainter objects, but also larger mirrors have higher resolution. And so we can see either smaller objects or we can see similar objects at a greater distance. So a number of different advantages for going for larger mirrors. So if there's always that advantage to go to large mirrors, you can ask the question, why, if we've got large telescopes on the ground, why do we bother putting a small telescope in Earth orbit? Well, it's all about getting above the Earth's atmosphere. And if you take a telescope the size of the Hubble, a 2.4 meter diameter mirror, the resolution would be degraded if you had a telescope of that size and placed it, even on a mountain top, if you placed it within the Earth's atmosphere and had it looking through the turbulent Earth's atmosphere rather than the unimpeded view it gets above the Earth's atmosphere. If it was at ground level, the Hubble Space Telescope or a mirror of that size, the resolution would be 10 times worse. Or if you like, the Hubble's resolution is 10 times better than you could get with a telescope of the same size sitting on the ground. So that's why we want to take telescopes and put them in space. And I'll return to the argument of space versus ground-based telescopes towards the end of the talk. So in terms of history, where did it all start? Well, we perhaps think of Hubble as being 30 years old. Indeed, it is the 30th anniversary of its launch or deployment. But in fact, Hubble started life in 1970. People were still stomping around on the moon when NASA were planning the Large Space Telescope, as it was known. The second milestone you can see is rather disappointing. 1974, they cancelled it. Basically, Congress said, this is a great idea, guys, but it's going to be too expensive. Scientists were up in arms. They were absolutely incessant and basically wrote lots of letters. That's how maddening it was to scientists. They started writing letters and eventually convinced the government to fund a space telescope. The Americans said, yes, we'll do this. We'll fund NASA to make a space telescope, but we need somebody else on board to help with the funding. So they got together with ESA, and basically it's a NASA-ESA project. A lot of people tend to think of the space telescope as a NASA project and sometimes forget the fact that it is actually a joint venture by NASA and ESA, even though NASA have put in a substantial amount of money. So by 1978, Congress had funded the Large Space Telescope and it went out to tender. The spacecraft construction was tendered to MA. So perhaps we think of it as a telescope, but NASA actually think of it as a spacecraft. It's a spacecraft that happens to have a telescope inside it. That's basically how it's viewed. So Lockheed took care of the physical construction and a lot of aspects of how it was going to be powered and guided, and the optical elements, the main and secondary mirror and other instruments were built by Perkin-Elmer. So if we move on a few years, by 1979, the construction of the primary mirror started. And there's a picture of the engineers at Perkin-Elmer inspecting the mirror. By 1981, the polishing was essentially complete and Perkin-Elmer declared the mirror was perfect. It was within specification. It was the best mirror that had ever been made. At that point, in 1981, work on a backup mirror was halted. Kodak were tasked with making a backup mirror because Congress realized that if you're going to make a space telescope, the primary mirror is absolutely key. And just in case there were any problems with Perkin-Elmer making that mirror, they said, let's have a backup made in parallel. So as well as Perkin-Elmer making the primary, Kodak were making a backup. As soon as Perkin-Elmer said, no need, guys, the mirror's fine, the mirror's perfect, Kodak were told, no need to do any more work. Your mirror is manufactured, polished, checked, and is also perfect, but we don't need it, so stick it in a museum. And that was the status of the Kodak backup. Come 1983, that was the original planned launch date. And at that point, the Large Space Telescope was named the Hubble Space Telescope in honor of Edwin Hubble, who of course had done so much pioneering work with the Hooker Telescope and the Hale Telescope in looking at the recession of galaxies and the expansion of the universe. There were a few slips in terms of the launch date from 84 to 85. By 1986, the budget had already gone beyond about $1 billion. And at that point, unfortunately, was the Challenger disaster. In 1986, one of the shuttles blew up on launch. and therefore there were no more launches for the next few years. And it wasn't until 1990, 30 years ago yesterday, that the Hubble Space Telescope was finally launched into Earth orbit. There was quite a backlog of different satellites that needed launching, so even when the shuttle fleet was operational again, Hubble wasn't very high on the list, and it took a few years to get it into orbit. At that point, the total costs were something of order $2.5 billion. I believe that doesn't include any costs of the planned maintenance of shuttle launches to maintain the Hubble Space Telescope. So you can see that it was a very expensive venture. And before we talk about exactly what the problem was with the mirror, it's worth just having a quick note about the design of the Hubble Space Telescope. I don't want to make this a talk about optics, but it is important to realize that the Hubble Space Telescope design is a so-called Ritchie-Creation design. Don't worry about those words if you've never heard of them before. What matters is that the primary mirror has a particular shape. It's called hyperbolic. You might be aware of certain shapes for mirrors like spherical or parabolic. This particular type of mirror is almost parabolic, but not quite, and it's made slightly off parabolic in order to deal with some of the aberrations that such a telescope would have. In fact, the last big telescope to have a parabolic mirror was the Hale telescope, the 5-meter or 200-inch mirror in the Hale telescope in Palomar Mountain. The Ritchie-Creation design was known back when the Hale telescope was put together, but Hale didn't want to do anything too avant-garde. He preferred to stick with a parabolic mirror, even though it was known that parabolic mirrors have certain aberrations. That was known, and he figured that they could deal with that. They didn't want to risk trying to make a more difficult shape, i.e. a hyperbola or hyperbolic. Think of hyperbolic simply meaning the shape of the mirror which is slightly flatter than a parabolic mirror. That's really all you need to know. But the important point is that a parabolic mirror will focus light from infinity to a point, but a hyperbolic mirror won't. You need two hyperbolic mirrors, the primary and the secondary, to work. We have to bear that in mind when we think about what happened next. Back in 1990, when Hubble was in orbit, they pointed it at a star, and it took them a while to realize they had a really serious problem. It would not focus. They thought maybe they had thermal problems. They thought maybe the secondary was in the wrong position, but they could not get sharp focus. Schematically, what they expected was on the left, nice, sharp star points. Okay, we still have lines through the stars, diffraction spikes, but that's perfectly normal. What matters is 99% of the light is focused down to tiny dots for the stars. But what they actually saw was most of the light was in a point, but there was a huge amount of scattered light, or what appeared to be scattered light, in a big halo around every bright star. In principle, it was around every star, but it was most noticeable around the bright stars. Eventually, they had to admit it was really serious. The mirror was made to the wrong shape. It had spherical aberration. Let's just make sure we understand what spherical aberration means before we go any further. If we imagine a mirror on the left, let's not worry about hyperbole and other things. Let's just imagine this is a mirror that should focus all the light to a point. If light hits relatively close to the center of the mirror, it comes to a focus at a particular point. If light hits the mirror slightly further away from center, it doesn't come to quite the same point. The focus is almost the same, but not quite the same. It's as if the focal length depends on where exactly you hit the mirror. And it gets worse the further away from the center of the mirror you go. So light hitting close to the edge of the mirror, like in the red line here, would come to a distinctly different focus from all of the other light hitting the other parts of the mirror. So this is a real problem. Where do you put your camera to get a nice sharp focus? If you put your camera there, for instance, at the so-called minimum circle of confusion, where most of the light is focused, you see light from the middle of the mirror focuses behind the camera, light from the edge of the mirror focuses in front of the camera. If you say, well, let's put the camera where most of the light is, if you put the camera there where most of the light is focused, you can see light from the edge of the mirror would produce a halo. And that is precisely what was seen. That middle image on the right-hand side shows you what you're getting. Most of the light coming to a nice focus, but light from the edge of the mirror is producing that halo. That's effectively how they diagnose the problem. So it's called spherical aberration because this is characteristic of a spherical mirror. Now, no one is saying that they made the mirror a sphere, but the word spherical aberration means this sort of aberration where light hitting different parts of the mirror comes to different focus. And that is the problem they had. The combination of the two mirrors, the primary and the secondary mirror, would not allow you to come to a unique focus where you would place the camera or the other instruments that you were using. So remember, the middle image is what they were actually observing. The bottom image is what they were hoping for. And just for comparison, the top image shows you what you would get for that sort of stellar field of view if the same telescope was sitting on the ground looking through a whole load of turbulent Earth atmosphere. It would blur the stars to the point you would see essentially what's in the top image. So they were doing slightly better than a telescope of the same size sitting on the ground. Well, yes, but taxpayers have just paid $2.5 billion to put this into orbit, because what we should be seeing is the bottom image. So saying that it's slightly better than what you would get if it was on the ground didn't go down too well with taxpayers or indeed Congress. So the mirror was made the wrong shape. How can you possibly make a mistake like that? Perkin-Elmer say that tests carried out during the construction indicated it was the best mirror ever made. Surface roughness of about 10 nanometers, 10 millionths of a millimeter. And if you want perspective on that, if you imagine the mirror was blown up until it was the size of the Earth, those roughness bumps, hills and valleys would be just a few centimeters in size. That gives you an idea of just how smooth this mirror is. It is exceptionally smooth, but it's the wrong shape. So how can they possibly do such a good job of polishing a mirror really smooth, but get the shape wrong by a huge 2 microns? If 2 microns doesn't sound like much, that is much larger than the wavelength of light, which is of order half a micron. So the bottom line is that the surface of the mirror was too flat. It was supposed to be a little bit flatter than a parabola. It was made a lot flatter than a parabola. And how can you spend that much money and get it wrong? Well, it's essentially because it's a difficult mirror to test. The mirror is hyperbolic. It needs a so-called null corrector. Again, we're not going to get stuck into the optics of what that means, but a null corrector is something you would use in a test rig to make, for instance, a hyperbolic mirror look like a much simpler shape. You can make a hyperbolic mirror look like a spherical mirror in order to test it. Or if you wanted to, you could make a hyperbolic mirror look like a parabolic mirror. It's effectively a corrective lens which is used to make the testing simpler. A null corrector was used, but the null corrector, a combination of mirrors and lenses, was put in the wrong place. The null corrector was off because a washer was placed on a bolt and it moved the entire set of optics about a millimeter. I think it was actually 1.2 millimeters away from where it should have been. Hence, Homer Simpson on the right. How could they possibly have made that error? Well, there was a big investigation. It turns out it was a sequence of errors, as always, but the bottom line is they used a laser interferometer to check the rig was set up correctly. The laser was picking up a reflection that they didn't realize was there because a fleck of paint had come away from one of the components, and they misread the positioning of the rig. A simpler test would have shown them that there was a problem. But Perkin-Elmer said there's no need for a simpler test. Our test is very sophisticated and it shows the mirror is absolutely perfect. No need for a simple test when a really expensive one will do. Easy to say in hindsight, but oh, that would have saved so much money had they done that. A test would have cost a few $1,000s to check that it was doing what they thought it was doing. The backup mirror, of course, is okay. The backup mirror was made completely independently by a different firm from a different piece of glass with a different polishing technique and a different test rig. And as far as we know, the Kodak mirror is absolutely fine. But it's in a museum, sitting on the ground, whilst the Hubble Space Telescope is 400 or 500 kilometers up in orbit. How do you save a mess like that? Well, it could have been an absolute and total disaster. If NASA or ESA hadn't been able to fix the problem, it's been conjectured that not only would it be very difficult for Congress to give any funding to NASA in the future, it's been speculated that if the problem hadn't been fixed, NASA may well have folded. Congress would not give any money to NASA ever again. So it is rather important they fix the problem. And one aspect of the Hubble saved it, and that was it was designed to be serviced by shuttle astronauts. They considered sending another shuttle up and bringing the Hubble down and swapping the mirrors, but that was actually rather more complex than it sounds. What they did have was what you see in the photograph here. They had a spare camera. There's usually a non-flight model of most instrumentation. So inside the Hubble is what we're going to call camera number 1. And sitting on the ground here is camera number 2, which is effectively a duplicate. So what they did was try and figure out why the mirror was wrong, how the mirror was wrong. They went back to Perkin-Elmer and figured out what was wrong with the test rig. So they know it's the wrong shape, but they know precisely what shape it is because they know how the test rig was set up. So knowing exactly what the shape of the mirror is, what they could do is effectively build in corrective optics into a second camera, a set of optics that would be known to work with the known shape, flawed, but the known shape of the Hubble's primary mirror. So that's effectively what they did. They put a correction into camera number 2 such that when camera number 2 was taken up, it would work flawlessly. Well, that's fine, but Hubble is not just a camera. There's a lot of instruments. So what they had to figure out is how do you correct the optics of all the other instruments up there? You can't swap out all of the cameras and spectrographs. There's quite a few of them, as we'll see shortly. So what they did is to say, what we need is a corrective set of optics that will correct all the other instruments. This particular set of optics is called COSTAR. There's a picture of the actual COSTAR on the bottom left. It's now in a museum for reasons I'll say later. It went up and then it came down again. And on the right, you can see a schematic of what it actually is, because it's a little bit complicated to look at the left-hand picture. The right-hand picture shows you that effectively COSTAR is a Swiss Army knife of corrective mirrors. Those colored arms are on little motors that move these little mirrors, the little silver discs you can see at the end. These are corrective mirrors that can be moved into the light path in between the primary and secondary mirror of the Hubble and between that and the instruments that are taking that light. So if you want to send the light to one camera, then either the red or the yellow or the blue arm would deploy and send the light corrected into that instrument. And if you wanted a different instrument, then one would retract and another one would fold out into position to send the light to a different instrument. So all they had to do was to fit COSTAR, and all that had to happen is that COSTAR had to work. There's not much space in there, so they had to sacrifice one of the existing instruments to get COSTAR to fit. And then in principle, as long as they did their sums right, COSTAR would then correct the optics for all the other instruments. As I say, there was an awful lot riding on this because they figured that if the astronauts made a mistake or if COSTAR wasn't designed correctly, or if the camera 2 wasn't designed correctly, if it didn't actually get it back to absolutely specification, then there would be a real problem. And here's just a reminder that although we tend to think of Hubble as being an imaging device, in other words, a telescope with a CCD camera, it's actually more complex than that. It's actually a lot more complex than that. At any given time, the Hubble has had at least 2 cameras and 2 spectrographs on board. In some cases, it had 5 instruments in total. And those cameras and spectrographs have been swapped back and forth by the shuttle astronauts on the service missions over the years. And we'll see some of the complexity of that in just a moment. Just as a point for those that are interested in astrophotography, whether or not we talk about the cameras being wide angle or high resolution, that really just is a question of the total focal length, and the nominal focal length of the optics in Hubble is about 58 meters. Bear that in mind if any of you have got a long focal length telescope. I'm sure it's not even close to that. If we blow up the picture on the left so we can see things a little more clearly, one thing to notice is that the Hubble telescope is actually only a small fraction of the overall length of the spacecraft. On the left, in an open position, is the sort of hood to stop the sunlight or earth light getting in. The secondary mirror is marked there, and you can see that's about a third of the way or a quarter of the way into the telescope. The primary mirror you can see marked there is about a third of the way from the right-hand side. And then around the primary mirror and behind the primary mirror are the various cameras and spectrographs. The spectrographs in particular are quite bulky, and they occupy a lot of space behind the primary mirror. So the primary to secondary distance is only perhaps 1/3, or maybe a little more than 1/3 of the total length of the Hubble Space Telescope. Okay, there's a risk that the next slide could get a little confusing, so bear with me or take a little 5-minute nap if you don't like this sort of thing. This is an indication of how complex the service missions were in terms of the shuttle flights to try and fix the problem. The horizontal bands here refer to particular aspects of the instrumentation. I'm not, again, going to describe exactly what they all are. The first one happens to be a camera. The other acronyms that you see there, if the acronym ends in an S, it's probably a spectrometer. If the acronym ends in a C, it's probably a camera. But also in there, you see two other entries, the third and the fourth, referring to the gyros and the electrical systems. That's because not only did the instruments themselves need occasional swap outs or repair, but also the gyros that are responsible for pointing the Hubble telescope in the right direction, and the electrical subsystems also needed a certain amount of work. So let's have a look at what happened in the first shuttle mission. That was Service Mission 1 in 1993. What happened? Camera 1 was swapped out for Camera 2. So we've thrown Camera 1 away and replaced it with Camera 2, which has got the necessary corrective optics so that Camera 2 should focus perfectly. The second instrument was thrown away. It happened to be a photometer to measure the intensity of starlight. Let's not worry about that. That got thrown away, and CoStar was put in its place. CoStar, the Swiss Army knife of corrective optics, is now responsible for sending corrected light to all of the other instruments. The little asterisk you can see on the next two lines simply means that whilst they were there, the astronauts gave a little tweak to the gyros and a tweak to the electrical systems to keep them running nice and smoothly. So that was the first shuttle mission. Everything ran quite reasonably for a few years. And the second service mission, SM2, kicked off in 1997. You can see no entries in the first four, but then one spectrometer was replaced with another. HRS was replaced with STIS. Let's not worry about what the difference is. But one spectrometer was replaced for another in both those cases. Given that it's only been up there a few years, why would you go to the bother of swapping out the spectrometers? Well, partly it's because we want ultimately to get to a point where each instrument has its own corrective optics to make sure it works effectively. But also bear in mind, technology moves on. Remember, this is planned in the 70s, built in the 80s, launched in the 90s. So by 1997, it's already old. And therefore, improvements could be made to both of those spectrometers. So in 1997, they effectively swapped out two old spectrometers for two new spectrometers. Okay. The third shuttle mission was just a minor one. It was just tweaking the gyroscopes. The gray you can see on the so-called NICMOS, one of the spectrometers second from the bottom there, the little gray patch indicated they started to have some problems in the early noughties. 2000, 2001, they had problems with that spectrometer. The fourth service mission, so-called SM3B, let's not worry about why it was called that, fixed that particular spectrometer, and they also swapped out the final instrument, one of the cameras for another camera, Sneakily, they put an S on the end, but ACS actually is another camera. And they've swapped one camera with another. So now all the instruments have their own corrective optics on board. Everything should now be working perfectly. Whilst they were there, they did a little tweak of the electronics as well as fix that spectrometer. This was 2002. A couple of years later was the sad destruction of Columbia on its way back from Earth orbit. And at that point, Congress said no more shuttle service missions to Hubble. Whatever state it's in now, that's the state it's going to be in forever. There was a bit of an outcry, not least because after a few years, some of the instruments started failing. There was a problem with some of the electronics and electrical systems. The spectrometer failed, the so-called STIS spectrometer failed, and even the relatively new camera that they'd installed only a few years earlier, that started having problems as well. So there was a very strong push from the scientists, please, one more shuttle mission before the shuttle fleet gets mothballed completely to get Hubble back in the state we want it. There was enough pressure on Congress to fund one final service mission. And in 2009, that final mission took place, SM4. Camera 2 was swapped with camera 3. Again, technology marches on. It's now 15 years of use, camera 2. They have a higher resolution chip in camera 3. And finally, COSTAR is no longer needed. We no longer need the Swiss Army knife of correction because all the instruments now have fully corrective optics to give Hubble the vision it should have had in the first place. So COSTAR was brought back to Earth, and that's the picture we saw earlier, now in a museum, and COSTAR was replaced with another spectrometer. So now Hubble has 3 spectrometers and 2 cameras. And the vertical row of asterisks there, you can see whilst they were there, the astronauts did a fantastic job of tweaking the gyros and the electronics and making sure that the 2 remaining spectrometers and the final camera were all working as well as they possibly could. To the best of my knowledge, nothing has gone seriously wrong since. So we've actually had a best part of a decade, more than a decade now, where everything has been effectively working as well as you could expect. People often ask, what is the life of the Hubble and how long will it last? What's the first thing to fail? Well, individual instruments may fail, but what is going to be absolutely key is that the gyros keep working. The gyros are responsible for pointing the telescope at the objects of interest. If you can't point the object for the camera to take its image or for the spectrograph to take its spectrum, then you have a white elephant back again. So hopefully the gyros will continue for many years to come. So let's have a think about the legacy. That is, after all, the title of this particular talk. What has it done for us? Well, in terms of science, can't possibly cover 30 years of science in only a few minutes. So let me just pick out 1 or 2 or 3 things that I think are relevant to what Hubble has actually done for us. Cepheid variables. This might look like a picture of the Milky Way, but actually it's a picture of part of the Andromeda Galaxy. I'm sure you're aware the Andromeda Galaxy is one of our nearest neighbors and is so large Hubble can't get it all in its field of view. But it can see a lot of faint stars in the galaxy. Some of these stars have been identified as Cepheid variables. These are variables whose luminosity varies according to a particular time structure, and the period of the variation is related to their luminosity, their true intrinsic luminosity, how bright they are. So if we look at the period of the variation of some of these stars in Andromeda, then we can determine what their luminosity is. And by looking at how faint they look, as well as knowing how bright they actually are, we can tell how far away those stars must be. So we can get a very good fix on the distance to Andromeda. And once Hubble had done that, our scale of the universe, if you like, which starts with how close are the closest galaxies and then moves out from there, we found that Andromeda was actually a little bit further away than what we first thought. So Hubble has allowed us to fix the distance ladder in terms of the nearest galaxies. And then there were different methods for fixing distances beyond that. But Hubble was responsible for getting that distance essentially correct. Hubble was also one of the very early pioneers of exoplanets. These days, perhaps we think of other specialist satellites like Kepler that are responsible for seeing lots of exoplanets. But Hubble was the first to image an exoplanet. This is a rather odd looking picture. There's a star at the middle. Most of the bright light from the star has been masked out. Otherwise, you wouldn't see what's in that inset in the right-hand side, which is a small planet which was imaged in 2004 and 2006. And you can see it's moved a little bit. So that's proof that there is a small object that is reflecting sunlight and is going round the star Fomalhaut. That's the brightest star in the constellation of the Southern Fish. This is the first time that it's been imaged directly. So we've got plenty of other indirect evidence of exoplanets. This was one of the earliest examples of direct imaging. And not only was Hubble able to take images of exoplanets, another very tricky thing to do for any ground-based system is to have the ability to image and take spectra of those exoplanets. So Hubble was actually able to measure the spectrum of various interesting exoplanets to determine whether or not there was water in the atmosphere of those planets, something that is very tricky to do with any telescopes these days, not only a telescope of the modest aperture of 2.4 meters for the Hubble. So a rather incredible result. Hubble has managed to image, I don't know how many thousands or tens of thousands or hundreds of thousands of galaxies, but by being able to get the resolution that we're not able to get from ground-based systems, Hubble has been able to image galaxies and allow us to get a much better idea of how galaxies work, how they evolve, how stars form within either the spiral arms or the other structures of various galaxies that we see. So not all galaxies are a spiral, of course. In this case, we have a rather odd looking ring galaxy where it's like a spiral galaxy, but it doesn't actually connect to the nucleus of the galaxy itself. It's like a spiral galaxy, but with an arm that just goes round in a circle rather than attaching to the nucleus. And the more of these galaxies that Hubble can image, the better our understanding of how these galaxies came to be. This, I think, is one of the most remarkable images that Hubble took. And let's see if I can talk you through it without actually being able to point at the screen, which is a bit of a limitation here. So we've got a galaxy in the center there, and that galaxy is actually quite a long way away. And between us and that galaxy, there are a few of these orangey fuzzy blobs that you can see dotted over the whole image. This is a supercluster of galaxies that is bending the light from this very distant galaxy and is producing more than one image. If I show you a schematic of what's actually going on in the next slide, we can see that the Hubble is on the left, the galaxy is on the right, and these large orangey galaxies in the sort of middle distance are bending the light. This so-called gravitational lensing is bending the light from this distant galaxy such that we see not only multiple images of the galaxy itself, but also we notice that there are four. Let me go back to the previous slide. You notice those 4 points of light that are pointed to by the arrows. This is not 4 supernovae that have gone off in this galaxy. Nobody's that lucky to get 4 supernovae going off at the same time. This is one supernova that's been imaged 4 times because of the gravitational lensing of the intervening galaxies. So not only can we determine that they're the same supernova by taking their spectra and determining that they are in fact all the same star, but if you notice from the light path that we see in this diagram, sometimes the path from the galaxy to Hubble is quite short, and sometimes that light path is a little bit longer. So you see perhaps in the top left-hand side there's an image of the galaxy. It's the same galaxy and it appears to be in a different place just because of the bending of light, but light is taking a little bit longer to get to us via that dogleg route. And so what the theorists were able to say is, look, we can see a supernova in the galaxy, as we can see in the bottom of this particular picture here. We can see that galaxy imaged 4 times, but light is taking a little bit longer to get to us via that other rather longer route at the top of the picture that we can see. So the supernova has already gone off in terms of our direct line of sight of the galaxy. But if we were to watch that other galaxy on the left-hand side, then in about 6 or 7 or 8 or 9 months' time, we calculate, because of that extra time it takes for that light to get to us, we should see the supernova go off. In other words, we've got advance notice of a star that's going to go supernova in a few months' time. And that's precisely what the Hubble was tasked to do, to go back and have a look at the left-hand galaxy, indicating that the light has taken a little bit longer to reach the telescope. And they went back a few months later. This was back in about 2015 or so. They went back a few months after the original observation, going off the same supernova which they caught, simply because of the time delay between the different path lengths of those light paths from the galaxy to the Hubble. So that ties in gravitational lensing, the formation of large superclusters of galaxies, supernova dynamics, and the ability to look back in time to different amounts by looking at different light paths. I thought that was an absolutely incredible result and an amazing combination of the experimentalists taking the data and the theorists trying to make sense of what was going on and make a prediction that you should be able to watch a supernova going off if you look at that galaxy in 6 months' time. An amazing prediction that did indeed work out. Perhaps you've all heard of the Hubble Deep Field. This is one of the earliest images. This was back in the 1990s, where they looked at a patch of sky in which, as far as they were aware, there was nothing particularly going on. In this particular image, they exposed for about 11 days. It was about 1 million seconds exposure, roughly speaking. There's a couple of stars in there, one on the left and one in the bottom left. I think that's about it. Everything else you can see there is a galaxy. So it gave us an idea of the scale of the universe. It gave us an idea of how many galaxies are out there. We're not necessarily catching all the galaxies in that particular field of view. It depends on how bright they are, but it gave us a good idea of just how many billion, how many trillion galaxies exist within our observable universe. Just to give you an idea of the scale, the image here gives you an idea of the size of the Hubble Deep Field on the sky relative to the size of the full moon. So you can see it's a tiny area, and if we're seeing thousands of galaxies in an area of that size, you can appreciate how many galaxies there are if we look over the entire sky. To make sure it wasn't a fluke, as well as looking at a particular patch of sky in the northern hemisphere, they also did an equivalent deep field by looking in the southern hemisphere. This is the Hubble Ultra Deep Field. They've also taken some more exposures, and now they're calling it the Hubble Extreme Deep Field, so don't worry too much about the labels. In all cases, it's a very long exposure of a patch of sky which was not thought to contain anything of particular interest, so it should be a reflection of what the entire universe looks like. Hubble has done wonders in terms of our ability to understand how light interacts with matter, and it's looking at images like this, where we're looking, as we mentioned before, the concept of gravitational lensing. Here we have some distant galaxies as well as some closer galaxies, which are the more orangey ones. And these orangey galaxies in the foreground are distorting images of some rather bluer galaxies. You can hardly make out those galaxies. They seem to be distorted into rings and arcs, some of which you can see in this particular image. By looking and analyzing lots of images like this, we build up a picture of how much mass is out there distorting the light from distant galaxies, and we come to the conclusion that there's far more matter there than we can see in terms of luminous stars and dust and gas. And images such as this over the last few decades have been instrumental in our understanding of just how much so-called dark matter is actually out there. Matter that is not luminous, does not shine, does not absorb light, does not generate light, but is responsible for distorting a lot of the light from these distant galaxies. It appears there's far more dark matter in these clusters than there is visible so-called normal matter. So although we have other evidence for that, Hubble is instrumental in producing a lot of the evidence. So I've been talking about its scientific legacy, but the Hubble has done so much more than that because it's brought the public along for the ride. Astronomy magazine said, wonderful quote, when referring to the pillars of creation and other nebulae, The laws of physics have created these incredible structures, and Hubble has revealed them. And through all the research, Hubble has brought the public along for the ride. It's taken the excitement that scientists feel with new discoveries and brought it to non-scientists. I think that encapsulates very nicely the idea that scientists are taking images and taking spectra for scientific reasons, but some of the results are so amazing, the public has really got on board with the whole thing, rather more so than you could argue for any other scientific instrument. So let's just have a look at a few of these images. This is just me indulging myself and having a look at some of the amazing images that Hubble has produced. The Helix Nebula, a wonderful planetary nebula with incredible structure. This is visible low down in the summer months in the constellation of Aquarius, but no amateur astronomer could hope to get the detail that Hubble has captured. Antenna galaxies, this is a pair of colliding galaxies where we see all of these regions in pink are regions where stars are being made effectively. So although galaxy collisions might sound very disruptive, and indeed it does to some extent disrupt the structure of the galaxy, it actually gives rise and starts to trigger an enormous amount of new star creation. So these two colliding galaxies are a very interesting study of how galaxy collisions produce star formation. A familiar image, some of what Hubble has imaged, of course, have been quite familiar to us. Some images have been quite new, some are old friends. But again, an amazing amount of detail in the Crab Nebula. One of my favorites is this one of Mystic Mountain. It looks a little bit like the sort of thing that you would see in the Pillars of Creation. It's in a different nebula. This is Eta Carina rather than the Eagle Nebula, but similar structures have been sculpted by the very high winds coming off some of these very young stars that are producing very strong solar winds and sculpting these nebulae. The Sombrero Galaxy, one of my favorite galaxies, not a very distinct spiral structure seen from this angle, but that dust rim that you can see around the edge is really stunning. The M5 globular cluster, this image is a reminder that in some cases telescopes struggle to resolve stars all the way into the core of a very dense globular cluster. And hence, in terms of analyzing the stars, you can only analyze some of the outer stars. With Hubble, it's able to resolve stars all the way to a core and hence, in principle, analyze many hundreds of thousands of stars within a cluster. Some spirals are so-called barred spirals. It seems that the Milky Way is a barred spiral, but the bar in the center of the galaxy is nowhere near as prominent as in this particular galaxy, where the bar is almost as long as some of the spiral arms themselves. Quite spectacular. Some galaxies are important for scientific reasons. Some are just extraordinarily beautiful. The Veil Nebula might be familiar to a lot of amateur astronomers and amateur astrophotographers, but who would have thought that if you get the detail right, you see structures like this. This is, for those that know it, this is the Witch's Broom, the Western Veil, or at least part of it. Again, the actual nebula itself is so huge, Hubble can't image all of it. So quite a few different wavelengths have been used to generate this image. The familiar Pillars of Creation, imaged back in the 1990s and then imaged again here with the new camera in for the 25th anniversary of Hubble 5 years ago. With a higher resolution camera, it produced a stunning image of the Pillars of Creation. And we've already seen the Hubble Deep Field. Again, it's one of the most remarkable images ever taken, given that although we take it for granted now, perhaps at the time, we really didn't know what would be imaged if you point the telescope nowhere in particular and then see what you get. So Hubble has got a fantastic legacy as far as the science and in terms of how it's effectively paid back the taxpayers for the past 30 years. But what goes beyond Hubble? We now have ground-based telescopes in principle that have adaptive optics. In other words, we can start to move some of the optics, bend some of the mirrors, if you like, to compensate for turbulence in the Earth's atmosphere. One way of doing that is, as you can see on the picture on the left, shine a laser into the sky. That makes an artificial star. And then you monitor that artificial star and see how it's wobbling. And you try and move the mirror, if you can do that fast enough, such that you compensate for the fact that the Earth's atmosphere is turbulent and is making the stars shimmer and move backwards and forwards. So if you can do that, you still need a space telescope? Well, you know, you look at the size differences. If you can use adaptive optics on a huge telescope, like a 40-meter telescope, why would you even consider putting another space telescope up with a much smaller mirror? Well, there are limitations. Even with adaptive optics, by shining a laser into the sky and using the blurring of an artificial star to tell you how turbulent the atmosphere is, you can only do that over a limited field of view. If you know how the Earth's atmosphere is moving in one patch of sky, it doesn't mean that the next patch of sky, 1 degree over to the left, is going to be doing the same thing. So if you want to get a sharp field of view over the whole of your imaging system, you can't do that with a single artificial star. So you can do limited work at high resolution with adaptive optics, but the advantage of a space telescope is you get pin-sharp resolution over the entire field of view of whatever your imaging system is. Let's just finish by reminding ourselves about other space telescopes that are in orbit. Kepler has now finished its mission, but Kepler, a NASA probe, had a very specific mission, and that was to find Earth-like planets orbiting other stars by looking at the dip in the star brightness as the planet moved in front of the star. And it did that by having a large detector, as you can see on the left-hand side, and the right-hand picture shows you the patch of sky it was looking at. Kepler was not scanning the whole sky, looking for stars that dimmed. It simply stared at one patch of sky, basically day in, day out, 24/7, and looked for stars that dipped in their brightness to tell them that an exoplanet existed. And Kepler has found thousands of exoplanets in that particular chunk of sky. And that gives us an idea of how many exoplanets are probably in the Milky Way galaxy. Gaia is another space telescope, not a very large mirror, but it has been able, because of a very large imaging system, to measure the positions of not just a few, but something of order 1 billion stars within the Milky Way. And it's measured their positions to phenomenal accuracy, not arc seconds, not milli-arc seconds, but something of order 25 micro-arc seconds. And it does that by imaging and re-imaging the positions of stars over and over again. Not only does that give you phenomenal accuracy, it also gives you an idea of how the stars are moving, their proper motion and their velocities. So we can get star positions and star velocities in the Milky Way, and that enables you to make a three-dimensional model of how the stars are put together in the Milky Way. And that's Gaia, which is still producing good data. If we finally reflect on the Hubble Space Telescope, excuse the pun, you see there a reflection in the astronaut's visor of one of the final service missions. Is there a successor for Hubble? Well, perhaps you've all heard of the James Webb Space Telescope. It's been just like the Hubble, it's had a very long gestation period. The Hubble was planned in the 70s, built in the 80s, launched in the 90s. James Webb has taken a long time to come to fruition as well. It's been in the final stages of testing for a while now, and it's hoped to launch in not too long, maybe a year or two. To give you an idea of the size of the James Webb, there's a comparison of the main mirror with the Hubble primary mirror. The Hubble primary mirror is about 2.4 meters diameter. The James Webb, well, it doesn't have a diameter as such because it's made from this segmented series of segments. but it's about 6 meters or so across, very much larger than the Hubble. Where is it going to be put? Well, it's not going to be in Earth orbit. The Hubble Space Telescope is orbiting 400 or 500 kilometers above the Earth, but the James Webb Space Telescope is going to be parked in a different place altogether. There are 5 places labeled 1, 2, 3, 4, 5, where you can park a telescope, or indeed any spacecraft, relative to the Earth and the Sun. And if you park it carefully there, it will stay there. So there are various so-called Lagrange points. The one of interest is the L2, Lagrange 2. That's where Gaia actually is. You perhaps notice from this little graphic, Gaia isn't actually sitting at L2. It's actually doing a little bit of an orbit. That orbital size is exaggerated. It's actually doing a little orbit around L2. There is physically nothing at L2. It's a mathematical point in space where if you put a spacecraft in orbit, it will stay there. It's about 1 million miles from Earth, and that's where the James Webb is going. And unlike the Hubble, it will not be serviceable. We've got no shuttles left, and therefore it doesn't make sense to have it serviceable. James Webb is going to be parked at L2, 1 million miles from Earth, to try and keep it away from the Earth and the Moon infrared sources, because the James Webb Space Telescope is an infrared telescope. Why would you want an infrared telescope? If we have a look at one of the classic pictures from Hubble, the Pillars of Creation, it's a rather nice image, but bear in mind that what we're looking at is the fact that we can't see through an awful lot of the gas and dust that exist in this nebula. If we were to take a picture in the infrared, we would see what's on the right-hand side rather than the visible on the left-hand side. You notice that the gas and the dust is now almost transparent. We can see inside the nebula, we can see what the stars are actually doing in there. We can get an idea of how those stars are sculpting the gas clouds. Not only can we see the start of star formation, we can see the early signs of protoplanets starting to be born around stars. Again, visible light, it's very difficult to see in the very dusty environment around a star in the early stages of solar system development. But if we use infrared, we can start taking a peek inside early solar systems to see how they're forming. Not only that, but remember the Hubble Deep Field, we're looking at a very large distance and hence a very large look back time. These objects might be many billions, it might be even more than 10 billion light years away, and they're moving at quite incredible speeds, a fair fraction of the speed of light. They're redshifted. In other words, as they move away from us, the light from the galaxies, the stars within those galaxies, is shifted towards the red end of the spectrum. That's what happens when objects move away from you. It's called the Doppler shift. And given that most galaxies have stars in them which are emitting mainly in the visible part of the spectrum, the faster these galaxies are moving, the more that light is being shifted out of the visible part of the spectrum and into the infrared. So although we can still see those galaxies, it's thought that they will be a lot brighter, especially the more distant ones, if we were to look in the infrared. So James Webb, as well as looking at nebulae and star formation and planet formation, the James Webb is also going to do this sort of deep field study, and hopefully those distant galaxies will be even brighter and we'll be able to look back even further than the Hubble was able to do. So although the James Webb is not a direct replacement for the Hubble in the sense that it's imaging a different part of the electromagnetic spectrum, it is hoped that it will be a worthy successor and will produce results that the Hubble was not able to give us. So I've given you an idea of why we need space telescopes and the limited effect that ground-based telescopes can compensate for the Earth's atmosphere. I've given you a little bit of background as to how the mirror was flawed and how the optics were fixed by the service missions of the Hubble astronauts. And I've said something about the scientific legacy and the public legacy that Hubble has given us. Thank you very much for listening.
Wow.
Thank you very much, Steve.
Excellent.
Yeah.
Thank you very much, Steve.
Okay.
That was absolutely superb.
Yeah.
Thank you.
Although I've seen the talk a couple of times before, it's always a good one to come back to, I think.
Can I just say, Mike, before I
Yeah.
kill the screen, that on the screen there's a web address. If
Yeah.
anybody would like the set of slides that I've used, a PDF with all of the slides, indeed quite a few more slides that I haven't had time to cover this evening.
Yeah.
If you go to that address or contact Mike or Dave or me later, and we'll pass on that address if you haven't got time to copy it down now. There you can find a PDF download of
Yep.
Legacy of the Hubble Space Telescope, which gives you all of the slides I've been presenting this evening.
Oh, Steve, what I'll do, I'll download them and I'll pop them on and a link on our website. Is that okay?
That's fine by me. Yep.
Fantastic. Yeah.
And I'll
brilliant.
put a link
Okay.
on the Go Space Watch site as well. Anyway,
Okay.
so
Thank you
okay.
very much. Excellent.
Yeah.
All right. Can I have my video back soon, Dave?
Sorry? Oh,
Oh,
we
right.
just-
Okay. I was going to say, is there any
Sorry.
questions? Sorry. Has
You need
anybody
to
got
start
any
your own, that's
questions?
it.
Oh, hang on.
I've stopped sharing. Should be back again now.
Okay. You stopped my video, Dave.
Yeah, you just restart it for yourself, Mike. I can't start it for you.
No, it doesn't work.
Oh. I've requested you start the video because that's all I can do.
Right. Oh, it's
there
back
you go.
now. It's back now. There it is. I've got it now. So, okay. Would anyone like to ask Steve any questions? They all mute.
They can unmute themselves if anybody's got any
Yep.
questions.
Hello, Rob. Hello, Sue.
Hello,
Hi, Steve.
Steve.
Hi, Rob. Hi, Sue.
Hi, Mike. Thank you very much, Steve. That was really good.
You're
Again.
very welcome.
Yeah, it's very good still.
As I understand-
Okay, if there's no other questions, what I'll do, I'll stop the live stream.